So now we are in chapter 4.1, which is exponential functions. Here are our objectives. And let's start with the definition of the exponential function. So the exponential function f with a base b is defined as f of x equals b raised to the x power. It's called the exponential function because x, your variable, is now located in the exponent, or inside the power. Therefore, hence the name exponential function. You can also write it as y equals b raised to the x power. B is a positive constant. He is greater than 0 and does not equal 1. And x is any real number. So here's an example of an exponential function. Let's say f of x was equal to 2 to the x power. B in this case is 2. That's greater than 0 and not 1. And x, your variable, is in the power. Here's another example. How about 2/3 raised to the x power? Again, b right here is your 2/3, who is greater than 0, and your x is found in your exponent. So let's go in our books to page 451. We're going to start by practicing problems 1, 3, and 5. And it says, approximate each number using a calculator. Round your answer to 3 decimal places. So number 1, we have 2 raised to the 3.4 power. So in your calculator, just go ahead and type 2 and then raise up the power. So depending on what kind of calculator you have, it would look like a caret key, which looks like this. And you raise it to the 3.4 power. So let's go ahead and do that. I shall do it too. So 2 raised to the 3.4 power is 10.556. Approximately 10.556. Let's try number 3. It says 3 raised to the square root of 5. So again, in your calculators, you're going to type the 3, use that caret key, and then it may be second. Well, all depends on your calculators. If you have questions on how to do things with your calculators, please email me. So it would be 3 raised to the square root of 5. And that square root comes from hitting the second square key. So let's see. 3 raised to the square root of 5 is going to be approximately 11.665. Okay, and then the last problem we're going to practice for now is number 5. And this time we have 4 raised to the negative 1.5. So again, in our calculators is 4 caret negative 1.5. 4 raised to the one second, trying to do this with my calculator. 4 raised to the negative 1.5. My calculator is telling me it's 0.125. Let me verify that. And yes. Alright, so let's keep going. So now let's talk about how do you graph an exponential function. So if we wanted to graph f of x equals to 3 to the x power, the first thing we want to do is set up a table of coordinates. So these coordinates are your x's and your y's. You choose x, so you choose x, and y, I'm sorry, I don't like that sentence. How about this? Choose x, plug into f of x to get y. Okay, so you choose the x, plug into your f of x, and y will come out. Once you do that, you'll have these points. Therefore, you must plot the points and then connect them with a smooth, continuous curve. Your exponential function has a curve to it. Alright, so we started this table. So here's our x's, and there's f of x. We've chosen x to be -2, -1, 0, 1. X is your choice because it's the independent variable. So you choose it. And then y is the dependent variable. It depends on x. So all you do is plug the x in. So 3 to the -2, well, that's 1/9. 3 to the -1 is 1/3. 3 to the 0, 1, and 3 to the first is 3. So you have your x's and you have your y's. So now you must plot them. Sorry, let's go back. Let's go back again. So now you must plot them. So -2, let's see, this is -2, comma 1/9. That's this point. This one would be -1, comma 1/3. This is 0, 1, and this is 1, comma 3. Plot your points and then connect them, making a smooth, continuous curve. Okay? Your exponential function never touches the x-axis. The x-axis is actually a horizontal asymptote for it. Alright, so now let's use the graph of f of x equals 3 to the x power to obtain the graph of g of x equals 3 to the x minus 1 power. Okay, so the best thing you should do is pick out at least 3 points. So pick at least 3 points, and then perform transformations on those points. Okay? Oops, why did I keep doing this to you? I'm so sorry. So pick at least 3 points and then perform transformations on those points. So this right here, this line that we see is the graph of f of x equals 3 to the x power. We must graph g of x equals 3 to the x minus 1 power. So let's think back to when we did transformations, and the difference between g of x and f of x is that -1, that -1. And notice that that change is on x. So it's a change on x, which means, remember, x did the opposite. If it says minus, it's telling me to go to the right. So this -1 is saying shift 1 unit to the right. Okay, remember, if the change is on x, you change it in the x direction, but you do the opposite of what you see. Because it says -1, we're going to shift 1 to the right, not to the left, to the right. So each one of these points, you would change just the x coordinate and you would shift it to the right. So -1, comma 1/3, that transformation will become 0, 1/3. Because remember, going to the right is like saying add 1. Let's put it this way. Add 1. Basically, do the complete opposite. And -1 plus 1, well, that's 0. And you keep the y coordinate the same. And then 0, comma 1, well, that becomes 1, comma 1. 1, comma 3 will become 2, comma 3. Okay, and then we have a graph here for us to look at. So the -1, comma 1/3 became the 0, 1/3. The 0, 1 became the 1, 1, and the 1, comma 3 became 2, comma 3. And then you're going to connect those 3 points again using a smooth, continuous curve. Alright, so now let's talk about some characteristics of the exponential functions. You will be responsible for knowing the first one, the second one, and the sixth one. Alright, so let's go through them. The domain of f of x equal b to the x, so the exponential function's domain, so his domain consists of all real numbers. So let's remind ourselves that domain means the x values. It's the x values of the function, the ones I can plug in and I expect to get something back. Well, b to the x power means x can be anything and I'll get something back. So your domain is the entire real line, negative infinity to infinity. The range of the exponential function consists of all positive real numbers. So it's 0 to infinity, not including 0. So the range are the y values. It doesn't matter which exponential function you graph, you'll only get out positive values if it's in this form. This exact form where it's b to the x, where b is positive. So you're only expecting to get positive numbers out, therefore you use a parenthesis because you are not including 0. Does not include 0. Alright, let's keep going. The graphs of all exponential functions of the form f of x equals b to the x passes through the point 0, 1. Regardless what the exponential function is, as long as it's in this form, it will go through the point 0, 1. Because x is 0, and anything raised to the 0 power in this class is 1. And that tells you that your y-intercept is 1. And there is no x-intercept. Remember, it never touches the x-axis. Therefore, if it can't touch the x-axis, it'll never cross it. Therefore, it does not have an x-intercept. And then I'm going to let you read through 3, 4, and 5. And let me skip down to number 6. The graph of f of x equals b to the x approaches but does not touch the x-axis. The x-axis, or y equals 0, is a horizontal asymptote. That's basically saying you will never get 0. So it doesn't matter what you plug in for x, you'll never get a 0 out. And you can try that. Pick different examples of exponential functions and see if you can ever get 0 to come out. It won't happen. So it never touches the x-axis. So you have a horizontal asymptote down here because y, which is your f of x, cannot equal 0. Not for your exponential functions. Alright, let's go in our books to page 452. And we're going to look at problem 29. And we're going to set this up, the complete problem together. And it says, begin by graphing f of x equals 2 to the x power. So let us start there. So f of x equals 2 to the x power. Well, if you're graphing by hand, you want to pick some x's, plug them into your function to get out some y's. So let me pick x to be -1, 0, and 1. And then I'm going to plug it in to f of x. So that's 2 raised to the -1 power, which is just a half. This is 2 raised to the 0 power, which is 1. And this is 2 raised to the first power, which is 2. So we have the points -1, a half, 0, 1, and 1, 2. So let's go ahead and, set up our graph. Let me label my tick mark. Let that be 1, which means you were 2, 3, 1, okay. Let me change colors. Go for green. So let's plot some points. -1, a half, maybe right there. And 0, 1 there. And 1, 2. Okay. So now let's make the attempt to connect the 3 points and make sure we have a smooth, continuous curve. There you go. Remember, it'll never touch the x-axis, so be careful. and then extend it all the way up and put an arrow on it. This is the graph of f of x equals 2 to the x power. Now, let's read the rest of the problem. Then it says, then use transformations of this graph to graph the given function. Be sure to graph and give equations of the asymptotes. Use the graphs to determine each function's domain and range. And you may use your graphing calculators as well. So number 29 has h of x. So h of x equals 2 raised to the x plus 1 power minus 1. Okay, so we have some transformations. And with transformations, you basically need to know what order do you start with. Well, it's just like order of operations. Remember PEMDAS, or please excuse my dear Aunt Sally, or any other saying they have for it. They started with parentheses, exponents, multiplication, division, adding, subtracting. In this case, who comes first? The change on x, because he's in my exponent, and then we'll focus on the subtracting 1. So whenever you're doing transformations, remember it's basically like your order of operations. Keep the same order. So the change first is on x. It's saying plus 1. Let me get... Okay, so that says plus 1, which means he's a change on x. I like that color. He's a change on x, and you must do the opposite. So you want to shift 1 unit to the left. Shift 1 unit to the left. Awesome. Now we get to look at this minus 1. How do we know that that plus 1 was a change on x? Because he's right next to x. As I tell students, if it literally is right in front of x, it is a change on x. Any other changes is on the function. That's how you determine it. If it's next to x, it's a change on x. Otherwise, this is a change on the function, who is y. So it's a change on y. And remember, the changes on y, you just follow them exactly how they say. This says minus 1, so we're going to go down 1 unit. So now let's make the changes to these points. That negative 1 in the x-coordinate, well, I know I had to shift 1 unit to the left, and that's the same as saying subtract 1. So we're going to subtract 1, so that's negative 1 minus 1, which is negative 2, comma, the half is in the y, and it said go down 1, which is the same as saying subtract 1. So a half minus 1 is negative a half. Good. Let's do the next. 0 is my x-coordinate. I must subtract 1, so that becomes negative 1, comma, 1 is in my y-coordinate. I must subtract 1, so it becomes 0. And then 1, comma 2 will become 0, comma 1. And let's go through and verify that one more time, because I am known to make mistakes. Negative 1 minus 1 is negative 2. A half minus 1 is negative 1 half. 0 minus 1 is negative 1. 1 minus 1 is 0. 1 minus 1 is 0. 2 minus 1 is 1. Alright, great. So now let's plot these points. And I need to give myself some more tick marks. There we go. So negative 2, comma, negative half. And I'm going to erase these numbers because they are going to be in my way. So negative 2, comma, negative half. It's just about there. We say that's halfway. And then negative 1, 0. And 0, 1. And then again, we want to connect these so they're in a smooth, continuous, I hope your graph looks better than mine, curve. And go straight up. And let's extend this out. But this time the horizontal axis has shifted, right? Before it was at y equals 0. That was the horizontal asymptote. Now, because we had to subtract 1 in the y direction, your horizontal asymptote, 0 minus 1, is at negative 1. So be careful how you extend this out as to not touch where y is negative 1. And this is your graph of h of x. Okay, then it said, give the equations of the asymptotes, which we have. Let's write it again. F of x has a horizontal asymptote of y equals 0. H of x has a horizontal asymptote of y equals negative 1. Remember, 2 to the x power has a horizontal asymptote at y equals 0. It will never touch the x-axis. And then when you shift h of x down a unit, that horizontal axis also goes down and it is at negative 1. And then it says determine the domain and the range of each function. So again, f of x, let's talk about the domain. Well, this is an exponential function, right? Therefore, its domain is all reals. Same with g of x, h of x. His domain is all reals. And then the range for f of x, well, the range says I want the y values, right? Well, y values go up and down. So remember, f of x is this green graph. What y's are included? All of these up here, right? But where do we start? We technically will never be 0, so it's parentheses 0, and then where do we go off to? Infinity. So it's 0 to infinity. And what about the range of h of x? Again, we need a place to start. How far do we go? We go to negative 1. We never touch it, so we can't include it. And we go where? Off to infinity as well. And that completes that problem. Okay. So now let's talk about the natural base E. E is named after Euler, who is a mathematician. The number E is defined as the value that 1 plus 1 over n to the nth power. This right here is added information for you. Okay? As n gets larger and larger, this value, this thing, approaches E, which is this non-ending, non-repeating decimal. It's basically special in this world. It's 2.718281827, and it keeps going. It never ends. It's an irrational number, and we basically say it's 2.72. He is the natural base. So your function f of x equals e to the x power is called the natural exponential function because you're using the natural base. Let's go in our books, back to page 451. Let's practice evaluating exponential functions using e. Make sure my calculator was set up. Good. So it says, let's start with number 7. And it has approximate each number using a calculator. Round your answer to 3 decimal places. So we have e raised to the 2.3 power. So in our calculators, let's do that. 2.3, hit the e. Depending on what kind of calculator you're using, if you're using the TI 83s or the 84s, or matter of fact, any TIs, I believe it's like this. On the left side of the calculator, you will see the LN button. Is it? Let me look at my calculator real quick. Yes, yes. You will see the natural log button. On that same button, you'll see small print, and it'll have e raised to the x power. It's small print, and like mine is blue, yours might be a different color. But to get e to the x, you must hit second, that ln button, and it'll come up with e to the e, and it'll open a parenthesis. So it should look like e parentheses, and then you fill in the number and hit enter. So e to the 2.3, let me do it again, is going to be approximately 9.974. And then let's look at number 9. It has e raised to the negative 0.95. Well, let's see what that is. 1 second. And it should be approximately 0.387. Let me verify these again. Yes. All right, let's keep going. All right, now let's look at number 39 on page 452. So again, we're graphing. And it says the figure shows the graph of f of x equals e to the x. So this time they gave us the graph. And they say, use transformations of this graph to graph each function. We're working with number 39. Be sure to give the equations of the asymptotes and use the graph to determine each function's domain and range. And of course, you may use your graphing calculators. And if you need help using your graphing calculator, send me an email and I will make a video on how to do so. So number 39 has h of x equals e raised to the x minus 1 power plus 2. And we need to do the transformation, right? So I am just going to pick some points, at least 3 points, right? So pick at least 3 points from the graph. You don't have to pick the same points as I do. I'm going to go for negative 2, comma 0.14. Also 0, 1 will obviously be there. We like 0, 1. And how about 1, comma 2.72? And let's do some transformations. Well, order of operations says the first thing we work with is exponents. So that's a minus 1. It's in front of it's by the x, which means it's a change on the x. So this is a change on x. And remember, you do the opposite. So this is telling us to shift 1 unit to the right, which is the same as adding 1. So we'll add 1. It's only the x coordinates, right? And then let's move on to the next, which is plus 2. Well, I don't see any x's around him, so he must be a change on f of x, which is y. So he is a change on y. And what is his change? He's telling us to go up. So the changes on y is exactly how they say it. So go up 2 units, which is the same as saying add 2. So let's make our transformations from our points. Negative 2 is in our first x coordinate, and it told us to add 1, so that will become negative 1. And then for the y, we're supposed to add 2, so that's going to become 2.14. Let's move on down to the next point. 0, 1 will become 1, comma 3. Make sure you're verifying that I'm correct. I do make mistakes. And the last point will become 2, comma 4.72. After you have your 3 points, you will plot them. So plot the points. And of course connect, making a smooth, continuous curve. I'm going to make a sketch. So it's going to be very basic and simple. I'm going to guesstimate without putting tick marks. Let's put some tick marks. There we go. -1, 2.4, there we go. 1, 3, and 2, 4.7. Looks almost something like this. And then connect your points. And be careful, the original horizontal asymptote was at y equals 0. By adding 2, your new horizontal asymptote is at y equals 2. So let's be careful not to go over the line y equals 2. So I'm going to put a dotted dash line there to help me. There we go. And go straight up. And this is h of x. So now let's finish answering the rest of the questions or the problems that they wanted us to do. Give the equations of the asymptotes. Well, for f of x, which was e to the x, his horizontal asymptote was y equals 0. For h of x, which was the e to the x minus 1 plus 2, his horizontal asymptote is now y equals 2. Make sure you're doing the shift, right? The domain of f of x, like any exponential function, is -infinity to infinity. You may include all x's. And the domain of h of x is going to be the same thing, -infinity to infinity. It's an exponential function. Now the range is what's different. The range of e to the x, if you look in your book, it is 0 to infinity, not including 0. That's the horizontal asymptote, right? You can't touch it. And the range of h of x is +2 to infinity. So basically, it is your horizontal asymptote, and depending on if you're going up, you put infinity, and if you go down, it's -infinity. Good. All right, last concept to talk about is formulas for compound interest. So after t years, the balance A in an account with principal P and annual interest R in decimal form is given by the following formulas. So, for n compounding periods per year, A, which is your balance, which I call it the future amount. So let's call this A is the future amount, what you hope to be in there, or what you hope to owe. So A is the future amount, equals P, which is your principal, like they said, and then parentheses means times. Now all of this is being raised to the nt power. So 1 plus R, which is your rate, and like they said, make sure it's in decimal form, divided by n, where n is the number of compounding periods in a year. It's the number of compounding periods in a year. And give me a second, after I explain this part, we'll go back to n. And all of this is raised to the n times t power, where t is just time. Okay, so now let us go back to that compounding periods thing. So if I told you that it is compounded monthly, so compounded, I'm going to abbreviate that as COM, monthly, how many months are in a year? 12. So in this case, n would be 12. And if I told you it was compounded weekly, again, how many weeks are in the year? 52. If I said it was compound quarterly, if I misspell something, you know, not my fault, quarterly, you'll figure it out. N is equal to, well, how many quarters are in a year? And if you don't know, think about how many quarters are in a dollar. 4. If it's compound semi-annually, well, semi means half, which means there are 2 of them. And then, let's see, am I missing any? Weekly, monthly, quarterly, semi-annually. What about compound yearly? How many years are in 1 year? Just 1. So depending on how they say it in the problem, n can change. So if you're dealing with compounding periods, you're going to use this formula. If you were dealing with continuous compounding, Like, they don't say exactly weekly, monthly, quarterly, semi-annually, or yearly. They literally say continuously compounding. You're going to use this formula where P is the principal, E is our friend, the base, the natural base, raised to the R times T power, the rate times the time. All right, let us go to page 452, and we're going to start by looking at problem 53, and we're also going to do problem 55. 53 says, use the compound interest formulas, the ones on the previous slides, to solve the exercises. Round your answers to the nearest cent, because we're talking about money. So it says, find the accumulated value of an investment of $10,000 for 5 years at an interest rate of 5.5% if the money is A, compound semi-annually, B, compounded quarterly, C, compounded monthly, and D, compounded continuously. I'm going to set up all of them, and I'm going to let you plug it into your calculators. Okay, so let's set up A through D. So 53, and remember this is an odd problem, so once you have it set up into your calculators, verify your answer by looking in the back of the book. If you get stuck, please email me. So the first thing we want to do is write down the information that they gave me. So the principal, how much I start with, is $10,000. I have a rate of 5.5%. And remember, write it as a decimal, so that's it's 0.055. And my time is for 5 years. And then part A says we want to do compound semi-annually. So compound it semi-annually. So right here we decide, well, N has to be 2. And then we just plug in the information. So A is going to be equal to 10,000 times 1 plus 0.055 divide by 2, all raised to the 2 times 5. All you do is fill it in. And when you're typing this in your calculator, depending on how you do it, you could type this entire thing, depending on your calculator, or you can do piece by piece, which means you'll work with parentheses first, then your exponents, and then you multiply. All right, part B says compound it quarterly. In this case, N is going to be 4. Everything else remains the same. So now A is going to be 10,000. 1 plus 0.055 divided by 2 raised to the 4 times 5. Part C is compounded monthly. So now we have A being 10,000 times 1 plus 0.055 divided by, let's go back to part B because I made a mistake, didn't I? That shouldn't be a 2 down there, that should be a 4. Divide by 12 raised to the 12 times 5. Now why did it change to 12? Because it says compounded monthly and N is equal to 12. And then the last one is D, and it says compounded continuously. So now we use a totally different formula. Now we have A equals, well, the principal is 10,000, E raised to the R times T. So 0.055 times 5 years. Okay, finish this problem for me. Let me know if you have questions on it. Let's look at number 55. And it says, suppose that you have $12,000 to invest. Which investment yields the greater return over 3 years? Basically, who gives you more money for your money? 7% compound monthly or 6.8 compound continuously. So let's see what information they gave us. Our principal money, the money we start with, is $12,000. We have time of 3 years. And the first one we have to look at is the 7% compounded monthly. So let's set it up. It says compounded monthly, which means we're using the formula A equals P times 1 plus R over N raised to N times T. I'm about to be interrupted. Nope, they'll come back. Alright, so we need to fill this in. We have the principal. We have the rate, which is 7%. N means compounded monthly, which means N should be 12, and T is 3. So P was 12,000. R is 0.07. N is equal to 12, and T is 3. So let's fill it in. We have A equals 12,000 times 1 plus 0.07 divided by 12, all raised to the 12 times 3. That will give you the compounded monthly. Again, I'm going to let you type that into your calculators. Now let's look at the 6.85% compounded continuously, which means it's a totally different formula, right? A equals P times E raised to the RT power. Again, P is the 12,000. We have the rate, and we have the time. There's no N in this problem because it's compounded continuously. So now we have A being 12,000. E, the rate has changed to 0.0685 times 3. Type both into your calculators and you decide which one gives the better return. You should come up with the 7% compound monthly being the better choice. You can verify your answers using the back of the book because this is an odd problem. If you get stuck, please email me. So this concludes our video for 4.1. Let me know if you have any questions.